Hi, welcome to Lecture 8 of CSBERG's Summer Workshops in Synthetic Biology. Here I'll touch upon some common metrics that we can use to evaluate model performance. But one major theme that I really want to emphasize in this lecture is the importance of being nuanced when interpreting and analyzing metrics that are reported by others, whether that's in the scientific literature or especially in the media. And as you'll soon see, the assumptions about our model and the assumptions about the underlying data distribution can heavily influence the numbers and the scores that are reported with these metrics. In addition, I'll try to bring in an ethical perspective and to see at what stage of the model evaluation process can we really leverage the benefits of ethical reasoning. So let's get started. Some common classification metrics are accuracy and error, sensitivity, and specificity. So let's get started by first looking at accuracy. Accuracy essentially is the fraction of all predictions that were correct, right? That's a simple definition, but suppose you have a machine learning model that reported 99% accuracy, okay, for example, cancer detection, and 1% error. Okay, so this seems like a great model. However, again, trying to be nuanced here, how can you really achieve 99% accuracy on, for example, this data set? Suppose you have 100 people and 99 of them do not have cancer, but one of them do. You can achieve 99% accuracy by effectively classifying everyone as healthy because you're just making an error one time in this data set of 100. So because of this imbalance in the data set we use to evaluate our model, we get a very misleading accuracy term. To correct for this, we can look at the sensitivity term, where it really means given that the patient is ill, what is the probability our model produces a positive reading? So here you can see it also expressed in a fraction of all those people that are truly, that actually have the disease, how many of them were predicted to have the disease. In our case, we're not making any predictions of the positive class because we're effectively saying everyone here is negative. So our sensitivity is going to be 0 and effectively corrects for this data set imbalance. And specificity does it for the other case. If we have an imbalance in that we have too many people in our data set that that have the disease and very few people don't have it. Now, you might be contesting in that, well, we shouldn't be evaluating our model on an imbalanced data set, but there are very rare cases where you can have a perfectly balanced data set. So to only look at the accuracy is clearly not enough. We really need to look at other terms that correct for this imbalance. Two other metrics for classification accuracy or performance evaluation are precision and recall. So recall, as you'll recall, is one of the definitions on the previous slide. And precision is slightly different. It's saying that out of all the predictions that were positive, what fraction of them were actually positive? Okay, I include these two definitions here because they are combined in the definition of the F-score. The F-score is a more holistic view of the classification performance of a model. So I encourage you to think about situations where even these scores can be misleading, perhaps due to imbalances in the data set or something peculiar about what a model is actually doing. Just a comment about F-score, usually don't see it in this form, but this is where you can derive the more commonly seen form of the F-score. Essentially, what's happening is it is a harmonic mean of recall and precision. You're sort of averaging these two terms in the F-score. How can we bring in ethics into evaluating model performance? Well, in many situations, the cost of a false positive will be different than the cost of a false negative. So consider this following scenario, where case 1, telling a patient that they have malignant brain cancer when they're actually healthy, and case 2 is telling a patient that has cancer that their test results are fine. So in the first case, this is a false positive, and in the second case, this is a false negative. These two mistakes that are made by the model clearly have different costs that have financial cost, emotional cost, and even cost of human life. So how can we weigh these two costs differently? Well, we can just multiply them by a scaling factor, alpha and beta, for each of these different mistakes made by the model, where alpha and beta are decided by the user, whoever is using the model. And the relative weights will be informed by ethical considerations. So perhaps you might think in this case that false positives should really be punished. No, actually false negatives should really be punished, because you're effectively telling someone who has cancer that they're fine, and you're not telling them the truth about their own health. So of course, false positives have their costs too, such as a financial cost or emotional cost dealt to the patient, but these things will all have to be factored into deciding what ways to use for alpha and beta. How does a machine learning model make predictions? Well, usually at least for machine learning models, you can use the output of the model and interpret that as a probability, i.e. the probability that a patient is positive for a disease. Probabilities are between 0 and 1. So here we see a curve that is the sigmoid function that takes in any value in the real numbers and outputs a value between 0 and 1 exclusive. Now, the sigmoid function is one of many functions that you can use, but effectively the model will output a probability, and that can be interpreted as the confidence that the model has in classifying the patient as positive. So for example, if the model outputs a value very close to 1, then that means the model is highly confident, very confident, that the patient has the illness. But what if the model outputs something that's very close to 0.5? That is sort of in the uncertain region, where you're not really sure what to classify the patient in, what bin to classify the patient. So this is the issue of choosing a correct threshold, right? Usually what happens is, okay, all of the scores above a particular threshold, for example, 0.7, all of those patients will be classified positive. Of course, you could be more nuanced and say that, well, there is an uncertain region where the model isn't really sure of what's going on. And in that case, we'll probably have human intervention. Okay, but the problem still remains how to pick this threshold. Well, we can actually do it by looking at a curve on the next slide. So what we can look at is this receiver operating characteristic curve, which is or otherwise known as the ROC curve. So incidentally, this was developed in World War II for detecting enemy aircraft and separating signal and noise. So the larger the area under this curve, the better the model. And what do I really mean by that? Well, let's take a look at what the curve plots. It's plotting the true positive rate versus the false positive rate. And just as a side note, this is a real curve that I obtained from a recent paper where they're classifying molecules as antibiotics or not antibiotics. Okay, so plotting this true positive versus false positive, let's take a look at the extreme examples where we have 0, 0, and 1, 1. So at 0, 0, we have no false positives. And how can you achieve that? You just classify everything as negative, right? You won't make any mistakes in terms of positives as you do that. And here for 1, 1, how do you achieve a perfect true positive rate? Well, you simply classify everything as positive, make sure you don't miss out on any positive, but you will have a false positive rate that's very high. So ideally, you want a high true positive, but a low false positive. And so the ideal curve, the ideal ROC curve, will look something like this. So straight up and straight across. And the area under that ideal curve, the AUC, ideally is going to be 1. In reality, that's never going to be the case, so you observe something more along the lines of this blue curve. And they quantified the AUC here as 0.896, which is fairly close to 1, indicating that it's a pretty good model. So, how do you interpret any point on this curve? Well, that's essentially changing the threshold, right? As you move in this direction on the curve, you're essentially becoming more or less stringent in your criteria for classifying something as a positive. Because as you move along this side, you're effectively increasing the false positive rate. But if you're moving along this way, you're becoming more stringent on what is a positive. So this is really, you need to sort of seek a balance in between, how many false positives do you want and how many positives can you afford to miss. So for example, for antibiotics discovery, false positives have an expensive cost because they, if the model identifies a molecule to be positive, it will then have to go through extensive wet lab experimentation to see if it's actually positive. Now we're going to switch gears a little bit and talk about Bayes' rule. But the underlying idea is still the same, where if you are not careful about your underlying data distribution, you could be deceived by these metrics that are reported. So let's take a look at this example where we're going to use Bayes' rule for lie detectors, i.e. polygraphs. So by the way, this example is from John Rice's statistics textbook. Okay, before we move on to the example, let's recall what Bayes' rule is. It's essentially just cross-multiplying rules that we know from conditional probability. So in the more general form, it's P of A given B, P of B is equal to P of B given A, P of A. And this is true because essentially both of these are equal to P of A and B. Okay, well, that's just a digression, but essentially what you can do is you cross multiply and you obtain P of B given A is equal to P of A given B, P of B over P of A. Here I just switch the symbols, T and plus sign. Okay, so what do these symbols mean? We're doing Bayes' rule for lie detectors, so the lie detector could give a positive reading, i.e. the polygraph predicts that the subject is lying. Okay, L is the truth, so L is the lie, but it's the actual ground truth of the data, i.e. this is the event that the subject is lying, and T is the event that the subject is telling the truth. And we are given these probability values where suppose the subject is lying, then we assume that the polygraph will give a positive reading 88% of the time. And in the other case, if the subject is telling the truth, polygraph will correctly give a negative reading 86% of the time. These two events are what you want the polygraph to actually do, right? And so you want these numbers to be high. 88%, that's pretty good, right? 86%. Now, just by looking at these numbers, you might think, okay, polygraphs are pretty accurate, right? So look, if I'm lying, it's going to tell me I'm lying 88% of the time. Well, the fact is, if you use Bayes' rule to calculate this value, you'll see something quite surprising, I think. So why do we want to calculate this value? The value is essentially saying, given that the polygraph has a positive reading, what is the chance that this patient is actually, or the subject is actually telling the truth? So i.e. the polygraph is wrong. What is that probability? Okay, let's see the probability. Before we get to the final number, we need to sort of make some assumptions on this value and this value. Okay, so this is just Bayes' rule again, but with the denominator expanded using the law of total probability. And I guess one intuition as to why the denominator is true is, well, essentially before this was P of plus, P of positive reading, but positive readings can come from either the test subject is lying or the test subject is telling the truth. So we essentially sum over both possible cases. Okay. Now, before we move on to the calculation, we assume that P of T is 99% and P of L is 1%. Intuitively, that just means we assume that most people won't tell a lie. 99% of people have no reason to tell a lie, and only those people who need to will lie. And that's 1% of the time, or 1% of the general population. Okay, so we have these assumptions. We plug these numbers in, okay. P of plus given T, this was computed on the previous slide. That's simply 1 minus 0.86, okay. And P of positive given L, that was an assumption from the previous slide. So computing all of this, you get 0.94, which is a high value given what this probability means, because it's saying that if the polygraph returns positive, there's a 94% chance the polygraph is wrong. And why is that the case, right? How come we had such good numbers on the last slide, but such bad numbers on this slide? Well, it's simply because of the underlying data distribution. So if you switch these numbers around a little bit, that is such as not this unbalanced or imbalanced, you will effectively reduce this error. Now, you might say that, well, this is not a good assumption to make, because if you're going to test people on the polygraph, you already have some suspicion that they might be lying, right? So this essentially might not be the case, but you can sort of think about cases where you do like general screening of the population for cancer, right? That's something that's routinely done. So these proportions are actually realistic for that situation. And so one test is clearly not enough, i.e. if you have a positive test, right, there's 94% chance your test might be wrong. And so you can sort of reduce this if you can't change this underlying data distribution by testing again, right? And repeated testing, if you have repeatedly the test tells you it's positive over multiple times, that dramatically reduces this error rate. Okay. We've talked about Bayes' rule, but there's this whole other class of statistical reasoning known as frequentist reasoning, where essentially there are some points of conflict between frequentists and Bayesians. So I'll try to explain these two and the differences between these two classes with a very simple example. So suppose you flip a coin 0 times. Okay, so you don't flip the coin at all. And I ask you, what is the probability of the coin showing up heads? If you're Bayesian, you would probably say it's 50-50 because you have seen how normal coins behave, and you have reason to believe that most coins would have a 50-50 chance of landing heads or tails. But if you're frequentist, then you would say, well, without actually doing the experiment, we can't have a say on what the probability is. Because frequentist, you base the probability on the empirical observations from the experiment entirely. Okay, now what does that really mean? Well, in Bayes' rule, you have something that's known as a prior, here mathematically denoted by P of M. Prior in the coin flipping example is essentially, well, I know that most coins have 50-50 chance, heads or tails. That's your prior. If you're going to use the frequentist mode of reasoning, there is no prior. Now, why is there this tension and this fight between Bayesians and frequentists? One point of many is this notion of a prior can be controversial, i.e., your prior might be different from mine. If you work in the casino, you might have seen more biased coins, right? I'm not saying anything bad about casinos, but in another case, if you're talking about priors on knowledge of the world, if you ask someone who was just born, their prior is going to be completely different than someone who is in their early 50s, for example. Well, we can sort of work our way around this issue. I'll try to bring up some solutions in the next few slides. But let's take a look at this equation before we move on. So P of M, as I said, is the prior. That's your prior belief on the probability of your model of the world. In this case, the coin flipping. But we have these other two terms that have their own definitions and labels that I think is really interesting to look at. So, well, before we talk about the left term, let's talk about this. This is the likelihood. And this is the posterior. The likelihood is essentially given your prior, given M, you fix that, and you evaluate the probability of observing whatever data you observe using the model that is encoded in your prior. So in the coin flipping case, you could have some prior that's centered around 0.5, but if you observe data, a bunch of coin flips that are not around 0.5, this will have very low likelihood. Okay. Then you're going to update your prior after observing your data. So that's going to be in the form of the posterior, where it's still a distribution over M, right, your model, but that is conditioned on data that you've observed. And so in the Bayesian mode of reasoning, you're effectively constantly updating your model of the world as you observe more data. Okay, so let's take a look at some commonalities actually between Bayesians and frequentists. So let's take a look at this example where we're flipping coins again, but we're doing it with a biased coin. And here they denote that parameter by alpha. So alpha is the probability of the coin landing on heads or showing up as heads, and that is 0.7. So this is a biased coin, and we want to sort of estimate this value by doing experiment. Okay, the top row is the frequentist approach, and the bottom row is the Bayesian approach. All right, so for the frequentist approach, or for actually both approaches, we're increasing the number of data points as we move to the right. So the two graphs on the left, this is where you have very little data, and the two graphs on the right where we have a lot of data, a lot of independent coin flips. So in the frequentist case, you can clearly see the estimation of the probability eventually converges to 0.7. Okay. One minute detail is that frequentists would not say they're estimating a true probability. They're simply observing the actual probability that is in the empirical data. So they're not really doing any estimation here. But we know the actual probability is 0.7, and it seems that they're correct after we observe a lot of coin flips. In the Bayesian case, we can see the notion of a prior being used in the form of this dashed line. So this dashed curve is the prior. And you can see the dashed curve gets lower and lower because, well, the scale is sort of expanding. So here, essentially, it's the same prior for all of these that has a peak around 8. Okay. But it's just that the posterior, which is denoted by this solid curve, is becoming more and more peaked as we increase the number of data points. And here we really observe the influence of the prior. So that mode of contention between frequentists and Bayesians is, well, the prior places too much of an influence on the actual results of the experiment. Well, here we can see that's actually not the case in high data settings or in large data settings. But that is the case when we don't have a lot of coin flips. You can see here that the prior effectively dominates the posterior. But as we increase the number of data points, the posterior is going to slowly shift toward the true parameter alpha. One conclusion to draw from this experiment is effectively when you don't have a lot of data, neither of these methods work well in estimating the true parameter. And in high data, or when you have a lot of data, both methods work pretty well, even with a strong prior, right? That is something that I also need to emphasize, is that our prior for the Bayesian case is very strong because it's peaked around 0.5. Effectively, the prior is, okay, I've seen many fair coins in my life, and I have reason to believe that this is also a fair coin. A weak prior, on the other hand, will be very dispersed, right? That looks like this. And the weakest prior is a uniform prior, where it's just 1. i.e. you're saying, well, any value of alpha is equally likely, and you're not placing heavy weights on any particular values of alpha. But that's what you're doing here. So you have a very strong prior, but that can still be overcome when you have a lot of data points. Now I mentioned frequentist mode reasoning, and one of the tools it has is to compute p-values. So before we talk about what's wrong with p-values, we need to understand what they are. So let's assume the null hypothesis. What is the null hypothesis? It's essentially the assumption that your control group is the same as your treatment group. Okay, so suppose that this black curve, this is your control group, and this is a distribution of some variable that you're measuring within all these, the people or the subjects in the control, and you have some treatment group that have data points that are clustered around this region here. Okay, what is the p-value then? You need to assume that you can model all your data, you can model your treatment group using the distribution in your control group. That's your null hypothesis. P-value is the probability of observing what you observe in your treatment, or an even more extreme outcome. So This will be made more concrete in the next slide, but effectively, if you have a null hypothesis that is shaped like the black curve, and you mostly observe data that's clustered around the tail, you'll have a very low p-value because your null hypothesis is not going to explain the treatment group well. So i.e., it's very unlikely that the null hypothesis is true. And what does that mean? That means it's very likely that the treatment and the control are actually distinct, that your treatment actually did something and affected this variable that you're trying to measure in both the control and the treatment. Okay, let's actually compute an actual example in the next slide. So we're going to conduct a very simple experiment and suppose that this is the data we observe. You toss a coin, independent coin tosses, a total of 12 times, and you observe 9 heads and 3 tails. You're going to assume the null hypothesis, i.e. the coin is fair. Okay, and so what are you really trying to see here? Is the coin not fair, right? That is the essentially the treatment, right? You can sort of think about it like that. Your null hypothesis is that the coin is fair. If your coin was unfair, you would have to somehow reject the null hypothesis by computing p-values. Okay, let's compute it in 2 different ways, 1 and 2. So the first way, let's just assume our data is generated from a binomial distribution. All right, let's walk through this. So on the last slide, we said the p-value is the probability of observing an event that is as extreme or more extreme than what you have in the data. So here we have 9 successes and 3 failures. So as extreme or more extreme could be 9 successes, 10, 11, or 12, all the way up to 12, because we tossed 12 in total. So we take the sum of these binomial distributions from s equals to 9 to 12. So let's sort of walk through what the binomial distribution means. You have 12 coin tosses, so suppose s is equal to 9. Then our first case is going to be 12 choose 9, i.e. you choose which 9 of those 12 actually showed up as heads. And so this is actually 0.5 to the 9 times 0.5 to the 3, where each of your 9 heads had a 0.5 chance of showing up heads because that's your null hypothesis, and the rest, the 3 other ones are tails. And together, you merge them together, that's 0.5 to the 12, and you take the sum all the way up to s equals 12, and you get a number. Okay, but let's assume we're going to use the negative binomial distribution to model our data. It's going to be the same data. We're using the same data. We're just choosing to use a different distribution to model. What is the negative binomial? It's essentially you stop until you observe a particular number of successes or failures. In this case, we can explain this data by saying, okay, stop the experiment until you observe 3 successes, 3 tails actually in this case. Okay, so let's compute the p-value. P-value again, any event that's more extreme or as extreme. But the negative binomial is interesting because, well, you can stop only when you observe 3 tails. That means you can have 11 heads, 12 heads, even 13 heads, 14 heads, maybe even 10,000 heads before you actually flip the 3rd tail. So here the summation takes s from 9 all the way to infinity, and the inside's a bit different, so let's go over that. When s is equal to 9, the first term is 11 choose 2. And why is it 11, not 12? Because you got a tail on your last toss. and that is your 12th toss. So that's fixed. You need to pick 2 more tails from the previous 11. So that's why it's 11 choose 2. And here is essentially how many are tails, how many are heads. Well, you have S heads, and always you will have 3 tails because you stopped at the 3rd tail. Okay, this number, when you calculate it, is 0.0327. And so what do you realize? These two numbers, these two p-values, are not the same. Even though you've used the same data distribution, you've observed the same data, you somehow obtain a different p-value. And that's only because you're using a different distribution, but what's even more troubling is that effectively you're using a different stopping rule. Because here in the negative binomial distribution, the choice of when to stop is actually encoded in that distribution itself. You're choosing to stop after you observe 3 tails, i.e. 3 failures. And by doing so, you somehow change the p-value, which is even worse if you're going to write something like p less than 0.05 for the second case and p greater than 0.05 for the first case. And then somehow arguing that this is statistically significant and this is not statistically significant. So if you want to read a bit more on the discussion behind this, highly encourage you to look at Kevin Murphy's textbook. Now, to summarize what these concerns are with using frequentist statistics in evaluating experiment outcomes, is that the decision of when to stop will influence the p-value. And that wouldn't be a big deal, but p-values are actually quite important in the scientific literature. So it is a big deal because people are making conclusions based on p-values. And so I will talk about issues with saying this p less than 0.05 in the next few slides. But essentially, when you're in a situation and doing, for example, a randomized clinical trial, this decision of when to stop influencing the p-value can become an ethical concern. Because if you already know that a particular treatment might be harmful, you might not want to stop that experiment for the purpose of computing a different or a more significant p-value, whatever that case may be. So again, relying on p-values to make decisions can be problematic. And this has been shown many times in the literature where the reliance on p-values is contributing to the reproducibility crisis in science. One example is where in 2011, someone showed that using p-values, using all the right math and using all the right calculations and tools that most people use in the literature, they show that we can feel the future. So we know what's going to happen 2 days from now, for example. Okay, so that's not conceivable, but they showed it anyway. And that's why analysis using p-values are banned from some medical journals. And the FDA, the Food and Drug Administration, is shifting to a more Bayesian approach in its drug approval process. But let's take a look at what's going on in this case. So, obviously there was controversy surrounding this claim that you can feel the future. So this is a paper that was published directly against saying that, well, all of their statistical analysis was correct, but really they should be changing the way they analyze their data. So even though the computation was correct, you really shouldn't be using these p-values and other tests that they did use to make these conclusions on extrasensory perception. which is what they showed to be true. Another ethical concern of using frequentist statistics in clinical trials or in drug approvals is this FDA requirement that all approved treatments must be effective 97.5% of the time. So what does this mean? It means that your p-value must be less than 0.025, i.e. less than 2.5% of the time, you will have essentially no significant benefit of your treatment from the control. So is this too strict? So a group of researchers at MIT argue that it is, and you can see the reference for this later. What they argued is for particular diseases that are severe and where few treatment options are available, such as pancreatic cancer, you should relax this criteria and propose an alternate false positive rate that is much higher than the current one. So right now, false positive rate needs to be less than 2.5%. They're effectively saying that for pancreatic cancer, it could go all the way up to 27.9% because of the severity of the disease. And so they have the severity factor where they included sort of like a weight to say the more severe and the less treatment options are available for a particular illness, the more open you should be to potential treatments to maximize the benefit to the patients. So as I mentioned, the FDA is shifting towards a more Bayesian approach to its approval process. And why are they doing that? And so here are some of the benefits that they outlined in a recent document on Bayesian approaches to clinical trials. So the most obvious benefit is that the use of the prior can allow the use of previous data as part of the current experiment. And a very good benefit of this is that it could reduce the number of subjects you enlist for your trial, and it could justify a shorter trial. Now, how do you actually incorporate this prior without sparking controversy? Well, one thing or one solution is to just base it on empirical observation, right? Previous data that are collected, those are actually observed evidence. Well, don't use the opinion for the prior. In addition, it can allow flexibility in the trial execution without changing the further downstream analysis of your model, right? So midway through your clinical trial, if you find that you're having trouble enrolling people for a particular arm of your trial, or you find that a particular combination of a treatment is actually harmful, then you can stop that early. You can stop that without interfering with downstream analysis tasks. And this has to do with the idea of Bayes' rule, where you update your prior as you observe more and more data. A more recent example of using p-values to assess effectiveness of a drug in clinical trial is Remdesivir. It's a potential COVID-19 treatment. So recently the NIH had a news release that said that Remdesivir does seem to be effective. So before we talk about that, let's take a look at some voices surrounding the use of p-values. And the main question is, should you be using p-values to make decisions? Wasserstein last year published a paper suggesting no, you shouldn't be using p-values to make decisions. In fact, you shouldn't even be saying that something less than 0.05 is significant, something greater than 0.05 is not significant. So they suggest that perhaps we should move beyond p-values into a world where this thing and this thing are not automatically in conflict, right? So not all data with p greater than 0.05 are just garbage and needs to be thrown away. And what's interesting is that they refer to this paper 1885, where Edgeworth, so he originally meant for statistical significance to indicate, this is some set of experiments or conditions that warrant further scrutiny, right? It is not an endpoint. It is not to say, okay, we have p less than 0.05, we're good, need to publish. So given that context, how should clinical trial results be interpreted? Now, we see that they do indeed cite p-values here, but they don't do it in a way that does saying like p greater than 0.05 for this case. So you see that they say the results suggest a survival benefit, right? And the p-value here is 0.059. So they did not throw this data away just because it's greater than 0.05. And so this issue becomes even more relevant around the margins, right? So what is the difference really between p equal to 0.049 versus p equal 0.051, right? What is this cutoff? What is the difference? And so, in this paper, they also outline 43 other papers that propose alternative solutions that can essentially be an alternative to just using p-values. And my personal opinion is that it is just unwise to make decisions based on one or two metrics alone. And you should really use an ensemble of metrics to come to a final conclusion. So here are the references. Highly recommend you to check out this paper, Moving to a World Beyond P Lec 0.05, and this is the document that the FDA published on the use of Bayesian reasoning in clinical trials. So I hope you learned something from this, and if you have any questions, please leave them down in the comments. All right, thanks.